Okay, yeah. So as I was saying, I'm Max. I'm a fourth-year PhD candidate in the math department. Mohammed's my advisor. I do algorithmic game theory. So a lot of this course material is pretty pertinent to the research I do. But I'm actually going to talk about something that's a bit outside the scope of my research, but it's kind of an interesting application of some game theoretic concepts as they make their appearance in most like top-of-the-line AI research. So I'm sure a lot of you have maybe heard about AlphaGo and AlphaZero. It's not really the hot topic it once was, just because the resurgence of all the open AI work and ChatGPT and DALL-E have kind of taken over the space of popular culture, artificial intelligence research. But we're going to take a step back. We're going to look at AlphaZero and AlphaGo and some reinforcement learning at high level, and yeah, how some of these game theoretic concepts came up. Okay, cool. So I can actually see this. Hang on. Okay, so in artificial intelligence research, I don't know, people can stop me if they have questions about anything. I'm kind of assuming some knowledge of like what AI is and how that actually appears in machine learning and whatnot. But a longstanding goal of artificial intelligence research is an algorithm that can learn from first principles, meaning that it learns from no base knowledge, and can exceed human intelligence. So obviously this is the holy grail of AI research. That's what everyone's working for. That's obviously kind of what ChatGPT is moving towards, is people trying to build this artificial general intelligence that can do a number of different tasks. In an effort towards this task, one of the first major instances of people seeing sparks of general intelligence was in 2016 with the work of the DeepMind group, which is kind of an offshoot of Google, where in 2016 they built AlphaGo, which demonstrated through using deep neural networks that were taught by human experts data, that a machine learning system can learn to exceed human intelligence on certain tasks, very specific tasks, but it was nonetheless very impressive, and we'll get in why that's actually the case. So the question is, in 2016, obviously they built this model that was trained on human data. And so one of the major tasks that came from DeepMind was, can we remove that human input and devise a network that can learn something from first principles and kind of generalize certain tasks to make a larger step towards these general intelligence ideas. So some background and motivation. So kind of stemming from this game theoretic notion. So the game that we're going to look at predominantly in this work, we're going to look at some other ones you probably talked about in class, but predominantly we're going to look at the game of Go, which is a two-player perfect information game. Does anyone play Go, or at least knows how Go works? Yeah, it's not very popular in this side of the ocean, but so Go is just a game that's played with two players where each person has a set of stones, either black or white, kind of similar to chess. And what you do is you iteratively take turns placing stones on this board. The full board is 19 by 19, but you can play on reduced instances. And what you do is you basically place your stones in a manner that you want to capture areas of the board. So if you surround a board or surround a section completely with your colored stones, then you've captured that area. And at the end, you tally up how much area you've actually covered with your stones. And then the winner obviously has a larger area covered. Naturally, this is a two-player game, and I don't think you can really generalize it beyond that. And it's perfect information. At each time, you have complete information over the set of space or the set of moves that the other person can't be making. So there's no loss of information there. So you might think that a two-player perfect information game is kind of the most idealized instance of a game that we have. So you would think that there should be a necessary solution to this game where you can kind of compute what the actual solution is from any given state, which tends to be the case with these two-player perfect information games. There's always a best strategy. But for the game of Go, this is actually not the case. So AI researchers have thought Go is a major stepping stone towards general intelligence for this reason, even though it's an easy game, because the rules are very intuitive to learn, and it's two-player perfect information. But actually, there's a lot of reasons to believe that this is a very highly intellectual game. And up until 2016, no computers could even really compete with humans. And the reason for this is that the branching factor for a game of Go is 250. So as a refresher, branching factor basically means from any given state of the board, how many different moves are playable from that position. So on average, it's about 250. For instance, like tic-tac-toe has a branching factor of at most 9, because from the initial start board, there's at most 9 moves you can make, but Go has a branching factor of 250. So in each step of the game, you're multiplying by another factor of 250. So there's no simple alpha beta search or max min strategy to kind of search over the tree of all the possible solutions. And with a branching factor of 250, this kind of makes the game pretty intractable from a standard sense, because there are more valid states to the Go board than there are atoms in the universe. So even with the best machine that we currently have, there's no way of searching over the feasible space to find the best possible move, at least in a timeline that's actually realistic. And the other factor is that there's about 40 million players worldwide. It's a very popular game, not so much in the States, but worldwide, it's a hugely popular game. It's kind of taught in schools a lot of the times, just as another kind of facet of learning research. It's kind of a hugely important game in other cultures. So that's why it's interesting. So we can go into some of the prior work. So I'm going to discuss some reinforcement learning and machine learning kind of ideas that you might already be familiar with. They're not really the most important. What we want to just like look at is the game of Go and the research and the results that we're seeing here. So I'm not really going to divulge. I'll show you some of the loss functions and the reason for their derivation, but we're not really going to be too interested with the mathematics today. Okay, so the prior work of AlphaGo, which was this first artificial intelligence that could play Go at a super intelligence level, ultimately relied on human data as input and a supervised learning at the start. So the way that this was initially trained to give this super intelligent system was a large corpus of training data was collected from expert players of Go. So specifically the data set look like this, where, oh, this is kind of low definition up here. So what the input trained data or the labeled data was that was used as input to the supervised learning system was a whole bunch of different instances of the Go board. So you see here just kind of a board with black and white stones placed on it. And it was labeled by what an expert would do given that board. So how they would place their stone. So you see here, kind of hard to see, but there's a red stone indicating from that given board state how an expert would decide to play. And so obviously what we want to do is train the neural network to learn to make moves in line with what an expert might do. Yeah.
So it doesn't care about any other time step. It only cares about the current board and what the next will do.
Yeah.
That's all it cares about.
Yeah, which is a limitation of this strategy specifically. Okay. And what we'll see is that when we move on, this isn't hugely covered in this talk, but that is a key factor of why this machine was able to be beat later on down the line, is that it wasn't really using a forward thinking kind of idea. So there's two aspects of how AlphaGo works. The first aspect is the supervised learning, where we have this training data. And basically what the neural network, what we call the policy network, tries to do is, given a board state as input, it tries to output a probability distribution over moves, where higher probability positions are what it believes to be what an expert is more likely to do. So this is kind of a visualization of this probability distribution on the 2D space, where these larger peaks are where it predicts an expert is more likely to play. And for this visualization, you see that kind of aligns with what the expert move actually is. So this first bit is purely supervised learning. It's just developing a neural network that learns from this training data. And then on top of that, what's built, and it's kind of the more interesting aspect, is a reinforcement learning approach, where after we've trained the network to learn these set of training data, what it does is it uses this policy network in a reinforcement learning system to instead predict the value of a given board. So what the value of a board basically means is it's trying to predict it's trying to quantify the likelihood of winning from a given board state. So after it's learned this policy network and it's trying to predict the best possible moves that an expert might make, it then it basically uses this policy network in play against humans and other bots and whatnot. And it uses a reinforcement learning type approach where when it wins, it kind of feeds back in and says, okay, what I did was correct. And when it loses a game, it decrements some of its weights. But what it's trying to learn is the value of given board states. It's trying to learn, if I see this current board and I play in the way that I know to play, what's the likelihood that I'm actually going to end up winning? And so from that, you can kind of feed back into the policy network, and you can learn new moves on top of what's already been trained, because just from playing over and over again, and obviously a computer system can play at a much faster speed and at a larger quantity than any human player can. So it can kind of learn on top of its already given expert moves to better learn the actual proper moves to win games. So this is just an overview, very high level of how the AlphaGo algorithm works. The policy network is trying to predict promising moves based on the expert data. So this is kind of a warm start, as we would call it in machine learning, where it's given some sort of pre-knowledge from humans. And then on top of that, it tries to predict how good a position is using reinforcement learning. So any questions on this general sketch? We're going to move away from this when we talk about AlphaZero, but this is really kind of at the basic level how AlphaGo beats humans. Cool. Yeah.
So AlphaGo and AlphaZero again.
Yeah. So we'll get into AlphaZero. So basically what AlphaZero is going to do is it's going to ditch all the human data. It's going to start from scratch.
Okay, so there are two separate.
Yeah, it's two different algorithms. Yeah. Okay, cool. And people on Zoom, if you have questions, just speak up whenever you feel I have you unmuted. Okay. So yeah, so for tree search, again, I briefly mentioned that the branching factor for Go is 250, so you can't do a tree search. But just as a reminder, because we're going to actually approximate this idea. In tree search, I believe it actually comes up in your homework this week, but it's basically this idea where from a given state, you look over all the possible moves that you can make, and you pick the one that's going to most likely lead you to a victory. So in the case, this is a basic tree search for the game of tic-tac-toe. So you see at the top level, you look at the space of all possible 9 initial moves you can make. And from there, if you pick one, you whittle it down to what the other player would do. And you kind of go back and forth between you and the other player until you reach a state where you see that I win. So if I'm playing as X, in this state, the winner is X. So you would do this for all possible moves. This is just an instance of one specific like DFS search on this tree. But what a computer would do for an easy game like this is it would search over the entire space of possible moves, and it would pick the one that's most likely to lead them to a victory. So over all the possible instances of the game, in what proportion do I win the game? And it's going to pick a move based on that. It's going to just do a maximization problem. So this is an exhaustive tree search, and this is feasible for tic-tac-toe. It's almost feasible for chess, but not really. We'll see that most of the algorithms here can generalize to chess as well. But so this is an example of that. But again, for a game of Go with a branching factor of 256 on average, this is no longer feasible. So we instead need to devise some sort of approximation to this idea where we can already initially just skip over moves that we think are going to be less useful. So we don't have to search the whole board space. So for approximating the tree search, the kind of major breakthrough here that is really the core of these AlphaGo and AlphaZero implementations that isn't really discussed too much when people talk about the literature on this algorithm is this approximation of the tree search. So what we basically want to do is for the policy network, where we're trying to predict the probability distribution over expert moves, we want to decrease the breadth. So in general, we don't want to have to search over all possible instances from a given board state. We want to be able to restrict it using this policy network where we already know, okay, experts are going to play in a certain way. So I can kind of remove from consideration these very silly moves that aren't really going to lead me to anything predictive. Especially with a board that's 19 by 19, there's a lot of moves that are necessarily going to make really no sense. So we're just going to remove them from our tree search. So that's how we decrease the breadth. And in terms of the depth with the value network, if we know prior board states that we're going to end up at, then we don't need to search the whole space of moves. Because at some point, we're going to see a space that we've seen before that's more likely to lead to a victory or a loss. So we don't need to necessarily search the whole tree. So these two ideas, this balancing of decreasing the breadth and decreasing the depth in order to get a better approximation for this tree search without actually having to do it. Okay, so this is just a visualization. We'll get back to that. So how the actual algorithm that's used to approximate a tree search is this randomized algorithm called a Monte Carlo tree search. And you'll see this come up a lot in modern reinforcement learning research because it's a very powerful idea. So there's 4 stages to Monte Carlo tree search as opposed to just searching the whole space of possible states for a system. So stage 1 is selection. So given these values that we've already estimated for a function that I can display here, so given a space of the possible moves we can make, instead of trying to make each individual one, we're just going to pick the one that maximizes our win rate and also ensures that each position can be selected. So in implementation, the algorithm that we actually use for that is this upper confidence bound algorithm. So basically, from a given state, you're going to have a set of possible moves you can make. And each one is going to have tallied a W sub I and an N sub I. W sub I is the number of wins that you've observed from that given board state. And N sub I is the number of times you've tried it. So you're going to be necessarily updating these parameters every time you play the game of Go. Every time you see a board state that you haven't seen before, you're going to update the values, or every time you revisit a position that you haven't seen or you have seen, you're going to update these values. And this T term is just the number of steps that you've played. So that's kind of the sum of all N sub I. And so in each stage, when you're starting your tree search, the first move you're going to look at is going to maximize this position. So basically what you're doing is you're saying, okay, is there a position that I've played many times and I've won many times? That's necessarily going to maximize this first term of the summation. And so then why would I search over those other moves that every time I play them, I lose, or I haven't searched them that much, so I don't have that much information on them? I'm going to restrict my attention to moves that I think are going to be beneficial. So this is the first bit. You want to select a move based on this. And from there, you will do this procedure down until you reach a state that you haven't seen before. So obviously, going back to this equation, if N sub I is 0, then the maximization doesn't make sense. You're dividing by 0. So you're going to do this tree search, this maximization selection, until you reach a state that you've never observed before. So you reach this board state and you need to expand your tree. You need to get an initialization for all your parameters of your objective function. And you're going to simulate. So you're going to take that move, and then you're going to play against yourself, and you're going to simulate a game, and you're going to see what's the outcome of that game. And from there, you're going to either win or lose this game, and you can update your parameter values, and you can feed those back up your network. And then this is this back propagation procedure. So I have done the tree search up to a point. I've reached a state I haven't seen before. I play a game with myself really fast to see whether I'm going to win or lose. And then, maybe that's not the best predictor of how the state's going to work, but it's going to give us values we can update in our objective function. And then you're going to back propagate that up your entire tree. So I can go into this more thoroughly if you want. I kind of went fast through this. Are there any questions on Monte Carlo tree search? Cool. It's a pretty intuitive idea. And nowadays, since this was 2016, you'll probably already see it in your AI or ML classes. But yeah. But the key takeaway here is that we're approximating the tree search. We don't want to do a full tree search. We're going to do it through some randomization procedure using the warm start from our training data. Yes, this is a more depiction of it. So you do this selection process where you just maximize our objective function until you reach a state that you haven't seen before. So that's this bottom of the tree. And from there you expand, which means you pick a move at random, and you basically run a simulation. So this squiggly line just means play a game, see what happens, and then you can update values back up your tree. So you can update your win rate and the number of times you visited the state. Such as the visualization of the Monte Carlo tree search. Okay, so now to get into some of the more interesting bits. So how did AlphaGo perform against human opponents after we trained it? So again, this was in 2016. And this is the first instance of a artificial intelligence playing the game of Go. Everyone thought that this was impossible for a machine to do because this game is so complex. And so in its second outing, I guess, it won 4 out of 5 games against Lee Sedol, who was the winner of 18 world titles. He was believed to be the greatest Go player to ever live. I forget his ranking. I think it was 9 Dan, which is like the highest a human's ever been. And the fact that he actually won one of those games is insane. It's so cool. If anyone is really interested in this kind of concept, I would recommend the book Maniac by Benjamin Labatut. It's kind of about this idea of how Lee Sedol played this move that was like so humanly intuitive that he won the game, and it broke down the entire algorithm. It's kind of insane, but AlphaGo did win 4 out of the 5 games, which was disheartening. And following further training, it won 3 games out of 3 against KG, who was later ranked #1 in the world, because Lee Sedol, after losing 4 out of those 5 games, he actually retired from Go. He said, "There's nothing left for me to do in this game," and he was very shunned away from the artificial intelligence. So then KG became #1 in the world, and he was like kind of taunting Lee Sedol. He's like, "How dare you lose to a machine? We're human. Clearly you messed up." And then he just got absolutely smacked by the thing. So 3 out of 3. There's a good documentary also called AlphaGo that's just on YouTube. I think Google made it. So it's a little propaganda-y, but it is a good breakdown of these games. There's some analysis of how AlphaGo actually picks its moves. So yeah, then the question becomes, this is the best algorithm in 2016. So how do we improve on the strongest Go playing agent in the world? So this machine beat all the humans we have that can actually compete against it. So where do you go from here? So the architecture in 2016 was 2 networks. There was the policy and the value network, like I discussed, which are convolution neural networks with 13 layers. It's really nothing too crazy. One of the more interesting bits, I guess, is that the training resources for these machines are immense. It's the Google computing power, and they can do anything. They can buy any machine, really. So the first iteration that was just trained using 176 GPUs, which we call AlphaGo Fan because it played against Fan, who is an amateur professional, kind of in the lead up to playing against Lee Sedol. It had an ELO rating of 3,000. ELO rating is kind of a metric people use for these games, just that to kind of relatively compare players. But so the first instance used 176 GPUs, which is a lot already. AlphaGo that beat Lee used 48 TPUs, so tera processing units, which is already an order of magnitude much bigger. And then they're actually able to slim that down for AlphaGo Master, which is basically just they rebuilt the machine on a new computer with 4 TPUs instead of distributed processing. They did it on a single processing unit. And this was 60-0 against professional players. It didn't play against Lee Sedol, but so basically they showed that if you give me a bigger computer, I can build a better unit or a better agent to play this game. But just increasing your actual computer and then being better is not really that interesting. So what they wanted to do instead is, so obviously the training time for these machines is around 3 weeks, which is a lot of devoted time to be using a TPU. And Google received a lot of pushback just in terms of the carbon footprint they made just from training these machines was kind of insane. So the question is, can we just reduce the complexity of this model? We don't want to use these huge machines. We want to have a lighter weight algorithm. Can we reduce the complexity of the training procedure that we're using and increase the generalizability? So even though we've played this game with an artificial intelligence that's never been done before, only by humans, maybe reducing complexity. This is this hypothesis that a lighter weight model will actually be more generalizable and be able to do more tasks. So going back to that original goal, the researchers at DeepMind kind of took a step back and they said, okay, can we build this algorithm without having to train it on this human expert data? So this is kind of the bottleneck procedure of the training time is when you have the supervised learning first bit, that's really not that interesting because you're just building a neural network to replicate what a human knows. So what they asked is, can we remove the human data? Can we extract all human features? And can we just build this with a single neural network that can learn to play how humans do and then beat us? And again, this is this idea of less complexity, we think, leads to more generalizability. And so the way that they did this is using the Monte Carlo tree search idea again in reinforcement learning, but how they trained the algorithm was removing all the training data from human experts. They just used self-play. So by this, I mean, starting from an agent that just plays at complete random. When it sees a board, it just randomly picks a move. It has no idea what it's doing. And what it does is it plays through reinforcement learning against itself. So it plays a game against itself initially where both it and itself are playing completely at random, and then one of them wins. And so they say, okay, something I did in there was right. So you're going to get a feedback loop where the networks are improved for, or the feedback from the system is improving. So it says, okay, I won based on something I did in this sequence. So it learns a little bit. And since it's a machine playing against itself, it can play against itself, hundreds, thousands of times very quickly. So what we do is the algorithm plays against itself. It learns through this reinforcement learning technique, or from this reinforcement learning technique in the Monte Carlo tree search. It plays 1,000 games with itself, and then whichever of the 2 instances of the same algorithm wins, we take that one and we repeat the procedure. And we duplicate and we say, okay, this was the winning agent. We duplicate it and let it play against itself. And again, we do this reinforcement learning procedure. And so over time, the algorithm continues to learn. So initially, again, it's just playing at random. But what it does is it later derives, okay, when I play this certain move sequence, I tend to win. So I'm going to keep doing that. And it's just iteratively learning just by playing against itself. All we've given it is the rules of the game. The rules being where you can place stones and basically how you score. So you would think, okay, it's just playing against itself. It's not going to learn anything too meaningful, or it's going to take a while to capture human knowledge. But what we'll see is that just replacing expert data by playing against itself is more than sufficient to completely surpass humans. So this is just a better visualization of what the neural network training is. So we remove that initial supervised learning policy network. And now basically what the algorithm does, it just looks at a state and it tries to derive a probability distribution over beneficial moves. And it tries to predict the value of each board state, where the value again is like the likelihood of winning from that state. So it's just one neural network with two heads. So it predicts a probability distribution and a value. And it learns entirely through reinforcement learning. And this is the loss function, which is pretty intuitive. You'll have the first term is just a squared error between whether or not it actually won and whether it predicted it was going to win, minus a log cross entropy for its probability distribution in terms of the probability of moves being beneficial versus how much it thought it was, and then an L2 parameter. That's not the most interesting bit, but so how did AlphaGo 0? We call it AlphaGo 0 or AlphaZero because it had no prior knowledge, had zero prior knowledge. So how did it actually perform in training? So what you'll see here on the x-axis is the number of days it was trained on. If you recall, AlphaGo was trained on weeks of training data, but we're just looking at days here. So at the 0th day, AGZ or AlphaGo 0 plays completely at random. Its ELO rating is terrible. It has no idea what it's doing. But within 3 days, AlphaZero surpassed AlphaGo. So AlphaGo was already the greatest player of the game to ever exist. Within 3 days, it was running circles around it. Within 21 days, it surpassed the iteration of AlphaGo that was trained for months, AlphaGo Master. And within 40 days, AlphaZero was the best player to ever play the game of Go. And again, this is no human knowledge. It's just learning from playing against itself in perpetuity, basically. And this ELO rating is like monotonically increasing. So the only reason why the ELO rating stops right there is because they just stopped training it. They felt no need to continue. In theory, it would just continue to play and learn and learn and learn until it's just completely unbeatable. And so just kind of as some more performance metrics. So the performance of AlphaZero throughout training as compared to other ones. So you see AlphaZero here is next to the raw network and then compared to the other iterations of it and kind of the first attempts at machine learning algorithms to play Go, which are really terrible compared to this. So what we see here is kind of the discovery of expert play opening moves. So these are sequences that, Go has been played since like 200 BC. People have been playing this game for forever. And these are opening moves that a lot of experts will play. You don't really need to understand them. But what was interesting is that throughout the duration of training, the researchers at DeepMind were trying to monitor when the actual neural network learned human moves. So this first opening right here, it learned within 4 hours, 5 hours, a game we've been playing for centuries. And let me see, I think there's a specific highlight. So this knight's move pincer, which is a move that, high-level amateurs or maybe experts might do to start a game, which kind of forces the players into a defensive mode. Initially, AlphaZero doesn't play it. So you see around the 20-hour mark, it doesn't really understand why you would do this. We're just plotting the frequency of the times that it actually uses this instance. You see around the 30-hour mark, it learns, oh, this is a good move. At around the 40 or 50-hour mark, it learns it's a really good move, so it does it a lot. And then actually around the 60 or 70-hour mark, it says, oh no, there's better moves. I'm going to stop doing this. So within, 2 days, it sees human moves and then it says, okay, we can do much better. I'm going to stop doing that. So we have a system that's able to surpass humans fully within 60 hours, 70 hours. So let's discuss more of AlphaZero. So how does the AlphaZero algorithm actually generalize across domains? So basically, researchers at DeepMind developed this idea of this self-play reinforcement learning, where a system can learn to play from just playing against itself and basically rediscover human knowledge. It's this idea. So they asked themselves, okay, with this new, less specified neural network that's, built specifically for Go, if we take this exact same neural network, we don't change anything about it, but we apply it to other board games. Can we also learn those board games? Is there any inherent complexity to, say, chess or Japanese chess, which is called shogi? And so this is, again, meant to be a validation of less complexity means more generalizability. So the first instance was using human expert data. So obviously it had to learn how to play Go. That's the only data we had. But using this idea of just self-play, can we learn other games easily? So to talk about chess a little bit, so chess is like the most widely studied game, especially in game theory and machine learning research. There's a lot longer line of research on computers that can play chess. IBM was one of the first ones. Turing, Shannon, von Neumann, they all love chess. They all studied it as a mathematical object more than a game. It's kind of like the Drosophila of the AI world. It's like the first sparks of intelligence we've looked at. Deep Blue, which I believe came from IBM, was the first computer algorithm to defeat the #1 ranked chess player in 1997. This was Garry Kasparov. But these algorithms are highly specific. So Deep Blue specifically, basically it just learned all possible sequences of the game of chess and then it just output the correct move from any given instance. So a lot of times when you play a bot on chess.com or like live chess, those algorithms have just memorized sequences. And chess is easier somewhat in that way because there's a lot of moves that when you see someone play something, you know what the correct move is to play in response. So this was just basically spitting out, regurgitating things. It didn't really learn anything. And in 2016, there was a stockfish, which again utilized domain knowledge and heuristics for the chess world. So there's a lot of human features fed in. So in particular, the following information was extracted and given to the system for training. So there's the board representation, there's bit boards, there's iterative deepening, aspiration windows, like a huge corpus of features that are extracted from the game of chess and fed into the system, so that it would learn to become the best chess playing agent. So that's not good. We don't want to be extracting all these features. We want the computer system to learn on its own. Yeah.
Is the stockfish still the leading AI?
Yeah. So stockfish is the gold standard that people use on chess.com just because people don't really implement AlphaZero online. But yeah, it is the leading one because again, it's very highly specific and it has all this information and it's static. Whereas these self-play algorithms are pretty dynamic. They continue to learn. So yeah, so again, there's all these huge corpus of features that we have to extract to train stockfish, which isn't good. So AlphaZero, on the other hand, we just, I say we as if I did anything. The DeepMind group uses self-play and reinforcement learning and just took the exact same network. They reset the biases and weights and fed it to play chess. We gave it the rules and like how you score basically a game of chess. And the following information was given, which was nothing. All it knew was the rules and like valid moves, and it had to learn from just playing against itself. So just some contrast between Go and chess to further extrapolate that this is a generalization step. So Go is translationally invariant. The move structure is very localized. There's a symmetry on the space. The action space is very simple. It's just a stone placement or not, versus the game outcomes, which are also binary. You either win or you lose. Versus chess and shogi, where there's no real translational variance. Moves in a certain area of the board are different from moves on a different area of the board. Moves are not necessarily local. For instance, the queen can traverse the whole board in one move. So you have to be aware of everything that's going on. There isn't symmetry because pawn moves are different at the start versus the end. The action space is conned down because you can move from and to, so it's directional. And the game outcomes are a little more complex in that you can win, lose, or draw. So it's a slightly different space of games. Yeah.
What is translational invariance?
Yeah. So translational invariance means like the value of a move in one area of the board versus another area. So in Go, the value is the same everywhere. Versus chess, you can
just moving the pawn up from 2 to 3 is going to be a different from moving the pawn from 7 to 8.
Yeah, right. There's different valuations. So it's a totally different game, even though it kind of looks the same on a board. But What we'll see here is that, so on the top left is the ELO rating for chess. On the top right is shogi. And then again, we have Go as just a baseline. And what you see here is that the ELO rating plotted in terms of iterations or steps of training. So for chess, it took 4 hours for AlphaZero to beat Stockfish, which again was the world champion in 2016. So 4 hours of training and it became the best to ever play the game. For shogi, it only took 2 hours to surpass the best agent, which was called Elmo. And again, using these new systems where we were training it, it only took 8 hours for AlphaZero to be AlphaGo. So it's pretty obvious that this reinforcement learning strategy, not only is it more interesting because it's totally from first principles, but it's also highly efficient compared to other training methods. And that kind of comes from the efficiency of being able to play against itself rather than have to wait around to play a human versus train on a whole corpus of human data. So the amount of search per decision. So for a human grandmaster playing chess, basically when they look at a board, they're probably searching over a space of 100 possible moves. That's just because human grandmasters are very good at this and they can kind of be aware of a bunch of different directions they can take a game of chess. So they probably consider 100. AlphaZero probably whittles that down to, or looks at the huge collection and whittles it down to a space of 10,000. Versus state-of-the-art chess engines will consider millions of moves. They'll consider every possible move before they make a decision. So not only is AlphaZero better than these AI systems in that it can beat them, but it also only needs to consider a much smaller range because it already, just through the self-play procedure, it's whittled down its space of possible moves. So it's obviously considering more than a human grandmaster because it has the capacity to do that. It's a computer, but it doesn't need to consider the whole board space. It's much more efficient. So to further illustrate that, we have the time per move. So when AlphaZero is considering a move for the game of chess as compared to Stockfish, you'll see that based on its relative ELO rating, so as it trains over time, it takes much less time to consider a move, and it actually, once it gets a bit more intelligent, it takes a bit longer, but not too much longer because it's kind of just weighing its options. And similarly for shogi, AlphaZero only is considering, given the amount of time it's allowed to actually use per move, it's much faster. So to kind of discuss the play style of AlphaZero, because you would think a machine that has surpassed all humans, it's probably going to be making these kind of very computerized moves, and since it's kind of cold-hearted, whereas a lot of people see Go as this very creative and human endeavor where people make moves that can be described as beautiful and very highly intuitive. So this is a quote from Yoshiari Habu, who was a 9-dan professional, which is like one of the highest ranks in the world. In studying the games of AlphaZero, he said that some of its moves, such as moving the king to the center of the board, go against the shogi theory. Again, shogi is like Japanese chess. From a human perspective, seem to put AlphaZero in a perilous position. It does these things that seem really ridiculous, but incredibly it remains in control of the board. So it has a very unique playing style, which is very aggressive in nature, and it shows that there are new possibilities for the game. And Garry Kasparov, who again was the world champion, was defeated by Deep Blue and then later retired as well. He said that he can't disguise my satisfaction that it plays a very dynamic style, much like my own, which is a bit haughty of him. I don't think it plays like him at all, but sure. So it is interesting, though, that we can see that a machine that's built from no human knowledge can rederive human knowledge and then also build new ideas on top of that. So that's kind of where we see these sparks of general intelligence, where we have an artificial intelligence that's able to beat us, but it's also able to teach us. It's able to learn new things we were not able to consider before. And that's kind of the inherent value. Obviously, a lot of people will say, why do you pour millions of dollars into research playing a board game? But it's exactly for this reason. It's kind of a proof of concept that we can have computers that can beat us and go beyond us and help us in learning new things. And a lot of people say that like the games that AlphaZero played against Lee Sedol, where it defeated the number one in the world at that time. People are still studying those games because there were so many moves that AlphaZero played that made no sense, but they worked out perfectly. So there's a lot of interest in actually just going back and studying how this machine performs. And I believe Lee Sedol now works at DeepMind. He's like a consultant. So he's probably just there studying how he lost. Yeah, ouch. And for those interested, you can see the publication from Google or from DeepMind on AlphaZero's play style and move selection. They did, their article doesn't really discuss the algorithm itself or the implementation too much, but it does go through individual moves that were pretty counterintuitive and kind of tries to analyze where it might have derived this information. So it's interesting on its own right. And I guess we can wrap up with some extensions and future directions. This lecture is probably going to be a bit shorter than usual just because the nature of this text. But so this work has already been extended with immense success to a bunch of other areas. In 2020, there was application of AlphaZero from a few researchers at DeepMind that showed basically AlphaZero can learn Atari games. So you can watch it. There are some great video visualizations, which I didn't include in this talk, but you can watch how AlphaZero plays Brick Breaker, which is where you have the paddle on the bottom and then the ball bouncing around. You have to break all the blocks. And you can see at the start, like the ball's coming at it and it just moves out of the way. It doesn't know what it's doing. And then later on, it like hits the ball once and it gets stuck in perpetuity beyond the bricks. And it's getting like the highest score you've ever seen. It's crazy. So it masters Atari games. It's learned Go. Yeah.
Isn't Atari more than not based, but rather it's like real time? So that's like,
yeah.
I just want to make a comment saying that sounds like a different kind of step up from Go to show.
Yeah, exactly. It's a totally different space. So it's really just the exact same work where it's not really learning through self-play. It's not doing a two-player game against itself, but it is just allowed to play a game and observe its own behavior. And it can learn through that in the same way. So it's still learning from zero principles. The only thing it knows how to do is move the paddle and observe whether it wins or loses. And so over time, it trains how it actually moves the paddle. And obviously it has like an awareness of where the ball is. It's just not moving it blindly, but it learns just from playing the game on its own, and it's able to play games at a much higher rate, and it learns to beat these games at the highest scores. So yes, this is another proof of concept for this reinforcement learning strategy. So it masters Atari games and Go and chess and shogi. And in 2020, there was also AlphaFold, which you may have heard of, where basically the same reinforcement technique was applied to protein structures. So given a chemical compound, deriving the actual structure of that protein is a very tricky task. Chemical researchers often have times where they have to put these things in isolation and kind of force them to denature and renature to observe how a protein actually folds upon itself. Because obviously there's a lot of different bonds taking place. There's a lot of different chemical interactions. And so the researchers at DeepMind formulated this as its kind of at its own form of a game, where there's like a minimization that would be the lowest energy state of a molecule. And obviously we have some data on chemicals that we know how they fold, but the AlphaZero framework of an algorithm was able to learn new protein structures as well as predict old ones. And so I think very recently they just announced some like new 10,000 protein structures that AlphaZero had discovered and had been validated experimentally. So it's truly helping us in like basic science research as well. It's predicting things that obviously need to be validated in practice, but it's learning new protein structures, and obviously understanding protein structures helps us develop vaccines and another number of different therapeutic treatments. So it already has very tangible real world impact just as a learning from first principles kind of reinforcement learning technique. And in 2019, some of the researchers kind of went off and taught it to play StarCraft 2. And it became the best player ever at StarCraft 2 as well. I think some people use it to play Catan, which is cool too. There's a number of different games. Basically, if there's a game, someone's probably tried to move it over to that game and see if it can play it. The StarCraft 2 is fun. I think there's a video of people, the DeepMind researchers taking it online to like league play and just beating people. And you can just like hear people on their hot mic getting absolutely flustered by this algorithm. But yeah, it seems like they're kind of just having fun with it now. But yeah, it's deeply fascinating to see. Oh yeah, and this is cool. So a very recent result, so 2022, they actually applied this reinforcement learning technique to learn the optimal magnetic control of a nuclear power plant. So in isolation, it was trained to, I'm not a physicist, I don't really know how this works, but there is some sort of fine tuning of the magnetism in a nuclear power plant to keep things stable. And it's obviously why nuclear engineers make a lot of money, because they're able to do this fine tuning procedure. And AlphaZero is able to do this. If you frame a problem well enough as a game with an objective function that's tractable, AlphaZero can effectively learn it. But that's kind of, I keep saying like DeepRL and this Monte Carlo tree search and all these things stacked together are capable of doing anything, which, you know, isn't necessarily true. So this is kind of a graphic to further depict this. So the guy says, this is your machine learning system. And he says, yep, you pour data into this big thing and pile linear algebra and collect the answers on the other side. And he says, what if the answers are wrong? And he says, you just stir it until it looks right. Mm-hmm. And that's kind of the nature of machine learning research. You kind of just push things around until you get the answer you want, which isn't the best scientific approach, but it is kind of what seems to work. Once you collect the right data and you have enough of it, you can kind of just push it in until you get the right result. So that's not the best thing. And there are obviously pitfalls to doing this approach. So one being the computational demands remain immense. Really the only one who can train a system like AlphaZero is Google. There are some lighter weight implementations that you can do on your own. On my GitHub, I believe I have like a very low level implementation that can play like 3x3 board games for anyone who's interested. But in large part, like when you want to have a system that can discover new proteins, like obviously every chemical engineer or like a biochemist is going to want that system, but it's not widely accessible. Really only Google can do this research. And obviously they're going to wait to be able to market something like this. So it's going to be a very for-profit scheme eventually. So that's obviously a very major pitfall of this research. In another regard, designing reward functions is in general a very non-trivial task. I'm sure anyone who's taken a reinforcement learning class, or you will eventually, half the nature of doing this sort of research is designing a good reward function. One that, you know, will have global or local maxima and minima. And so for games like, you know, AlphaZero or chess, it's a bit more easy because you have a win or a loss outcome and a natural state of moves to be making that you can maximize over. But designing reward functions for something like protein folding is highly non-trivial. So the fact that they were able to do this is interesting in its own right, but a lot of problems that we face in our daily lives that we would want, you know, maybe AlphaZero to help us with, don't necessarily have a good reward function that we can minimize or maximize. In the same regard, most data is not so clean. For a lot of these problems, it's hard to get the right feedback that we might want. Obviously, again, for board games, we have a very binary outcome that's very helpful to feedback into our system. But for a lot of spaces, that's not really that feasible. And in actually defining problems, that's also a non-trivial task. So when we define the problem of chess and shogi, we basically just feed in the rules of the game and the space of feasible moves you can make from a given position. But for a lot of problems we're actually interested in, it's hard to define the space of moves and the space of possible decisions you can be making. So yeah, those are some natural pitfalls. And I believe that is the conclusion. So here are some of the references. If you have any questions, I'm happy to answer them now. But yeah, that's a high-level overview of a very computational approach to a lot of game theoretic concepts. Thanks. Any